Hello, class. Today our goal is to give a bunch of families of graphs that you can refer to and use as examples to look back to when we're looking for things. So let's start with the most boring possible graph. And so every graph is going to have some set of vertices. And they don't have to be called 1 through n. We could label them in other ways. But you could ask yourself, what's the most boring graph we could have on the things 1 through n? Well, I need to choose some edge set. Remember, that's a subset of v choose 2. Well, I could always choose this to be the most boring set of all, namely the empty set. And so if you want to picture what this graph would look like, I'll call this the empty graph on n vertices. This is just n dots floating around in space with no connections between them at all. And so if I want to refer to this graph in the future, I could denote this by empty set sub n. This is the empty graph on n vertices. That's not a super interesting graph. Okay. Next, I want to talk about what we're going to call the cycle graph. Okay, here we're also going to have as our vertex set 1, 2, up to n. And what we're going to do is we're going to join each point to its neighbors. So we'll basically, as the title suggests, put these things in a cycle, up to n, and so we'll connect 1 to 2, 2 to 3, 3 to 4, 4 to 5, all the way around. And then we will, at the end, connect n back to 1. So my edge set here I can give explicitly as the set 1, 2, 2, 3, 3, 4, n minus 1, n, and then lastly, for good measure, we'll throw in n1. Okay, so there is our cycle graph. And so, for example, if we write down, I'm going to denote this, by the way, by c sub n. If I write down, for example, c4, that's going to be a square. And so there's 1, 2, 3, 4. 1 connects 2, 2 connects 3, 3 connects 4, and then 4 connects back to 1. Okay. I'll note here, in order for this to really work and make sense, I need n to be at least as big as 3. If you try and draw the cycle graph on 2 vertices, you don't really get a cycle. I try and say, okay, I'm going to connect 1 to 2, and then, well, this last instruction would say connect 2 back to 1, except now I have 2 edges between the same pair of vertices, and at least in our default definition, we're not allowed to do that. So that is our cycle graph. You might notice that this sort of mirrors the structure that we talked about back when we talked about sitting people around tables earlier in the course. And when we were doing that, we often talked about how there is sort of rotational symmetry involved, and we sort of figured that out. And so one thing as we sort of talk about a lot of these graphs, we'll again be talking a lot about the symmetries of these various graphs. And so this graph, for example, has that rotational symmetry. And in fact, for any n, this will have that rotational symmetry of sitting n people around a table. But if you look, actually, it will also have that mirror symmetry where you flip it over. And so, in fact, actually, if you were to write down the entire set of symmetries of this particular arrangement, it would have 8 symmetries corresponding to the 4 rotations, including the rotation where you don't do anything, and then the 4 rotations after you also flip it over. And so, in general, actually, the cyclic graph on n vertices, it always has 2n symmetries. And for those of you who have taken abstract algebra, you will identify that those 2n symmetries are exactly the elements of what in abstract algebra is called the dihedral group. Okay. next up, I want to talk about what is called the complete graph on n vertices. Now, the word complete starts with a C, but so does the word cycle, and so I can't call the complete graph C, and so I'm going to do the same thing that economists do when they have a bunch of different words that start with C, and you want to do another thing. Namely, I'm just going to call it K sub n, because K, I guess, makes the same sound or whatever. Maybe in German this word starts with a K. I don't know. But anyway, the complete graph on n vertices. And what the complete graph on n vertices is going to be, this is going to be the graph where I have my vertex set is 1 up to n, and my edge set is actually all of v choose 2. Namely, every pair of points is connected. Okay, so if I draw K4, I will connect these. Okay, and I want to note that this is actually the first time I think I've drawn a graph where the edges cross. And I want to note that has no mathematical significance, that the way I've drawn this line goes across this line. There's not a vertex here, so this is nothing. In fact, actually, if you wanted, if you were a little creative, you could say, okay, that was a bad way to draw that. I'm going to actually draw that line over there like that. And now it's the same graph, and now actually there are no crisscrossing lines. But in general, if the lines crisscross, they crisscross. It's fine. We don't have to pay any attention to it because, again, all we care about when we're describing the structure of a graph is what pairs of points are connected and which pairs of points aren't. Just be aware that if you're not super clear when you're drawing your picture, if you have lines that cross, it might trick you into thinking there's a vertex there when there's not. So, in a very real sense, this is the opposite of the empty graph that we talked about before. And I'll note this whole game we played with this blue line where we sort of moved it off so that none of the lines crossed each other. That's a game we're going to play later, because one of the things we're going to call or talk about is this whole idea of planar graphs. And a planar graph is one, and don't bother thinking too much about this now, but a planar graph is one where it's possible to draw it in such a way that none of the lines cross, like all the graphs we've talked about so far. Okay. A couple more examples that I want to have always at hand for us. And so the next one I'm going to talk about is the complete bipartite graph. And so this is going to be indexed by two numbers, m and n. And so my vertex set here, the way I'm going to write this down, is it's going to be 1 up to m in blue, and then 1 up to n in red. So that means, just to be clear, 1 blue and 1 red are different, so this vertex set has size m plus n. And I'm going to draw this, so I'll draw, I guess, the blue vertices first. So here's 1, 2, 3 blue vertices. Here are 3 red vertices. And so this thing I'm going to draw a picture of, this is going to be K3, 3. And the way the complete bipartite graph, I'll write that over here just to remind you, that's the thing we're talking about, complete bipartite graph. The way a complete bipartite graph works is that we connect every blue vertex to every red vertex. So we'll do something like this. And then that, like that. So, for example, in this case, the edge set has size 9. You can figure out what, in general, the size of the edge set is. But my edge set is basically the set of all blue point, red point. Something blue and something red. Okay. So this particular graph, K33, this is often known as the utility graph. So this specific one is called the utility graph. And the reason why this is often called the utility graph is because there is this question that you often get asked as a youth, where someone says, okay, let's imagine that we have 3 houses. So we have up here, we have house 1, and then we have house 2, and then we have house 3. And then down here at the bottom, we have 3 utilities. So we have the power company, we have the water company. I'll attempt to draw something that looks like water, even though I'm drawing it in red. Okay. And then we have the sewage company, or whatever. I'm not going to draw a picture for that. You can imagine what that looks like. Okay. And then the question is, can I connect all 3 utilities to all 3 houses if I say that the connections can't cross? So you might start, for example, saying, okay, I'm going to connect the power to everyone first, and then I'm going to connect the water over there, and up there, and over there, and then I'll connect the sewage connection there, and then the sewage connection there, and then maybe I realize that, oops, I have prevented myself from finding a way to connect the sewage to this last house. Okay. And so then, I guess the idea is to occupy lots of children's time. They can then say, okay, well, what if I'd drawn this differently? What if I had done this other thing instead? And so eventually you might come across either a way to do it, which you won't because they wanted to keep the children busy a long time, or you'll come across a proof that you can't do it. And so we'll do that later in the course. Now, an interesting thing, and I'll put a link in one of the videos descriptions, is that if you drew this instead on a coffee cup, then it becomes possible. Or if you prefer, if you want to imagine that instead of living on a boring old sphere, if you want to imagine that your 3 houses are situated on the surface of a torus, then it becomes possible, in fact, to connect all of these things. Okay, so the last example I want to talk about is what's called the Peterson graph. This is actually not a family of graphs. This is just a specific graph, but it happens to be an incredibly useful sort of generic graph to have in mind. So when someone gives you any definition for a graph, this is a very good place to start with, is the Peterson graph. And so here is the Peterson graph. So the Peterson graph has 10 vertices, which you cannot see if I write over there. It has 10 vertices. You can see that. And it has 15 edges. Again, notice red and blue have been used here to emphasize to you that the vertices are clearly these 10 points, and so the places where the lines crisscross are not vertices unless there's a red dot there. Now, this graph is interesting for a lot of reasons. One of the reasons is that this graph is very highly symmetric. So this way of drawing the graph has made clear that there's a symmetry of order 5, meaning I could rotate this 5 times around, and that would definitely give me some symmetries. But I could draw the same graph not like that, but instead like this. Now, it will take you a minute to convince yourself that this is the same graph as that, just in a different order. But if you imagine that you could take your finger and drag these vertices around, you can spend a while figuring out how could I drag those vertices around to get them to look like this. And indeed, you certainly can. And you can check some basic sanity checks to see that that seems plausible. Like, for example, there should still be 10 dots if there were 10 dots before. And there are still 10 dots. There are still 15 edges. It's still the case, in fact, that every dot has 3 lines coming out of it. But it will still take you a bit to figure out, okay, I could draw this like this. But what's the advantage of drawing it like this? Well, if you draw the graph like this, now it's apparent that there's a symmetry rotation of 3 things. If you rotate this 120 degrees, you get exactly the same picture again. And so not only does this thing have a symmetry of order 5, it also has a symmetry of order 3. Okay, or you could also draw the same graph this way. And at first, this picture looks highly asymmetric. And so you might think like, oh, this doesn't show me that this graph has any symmetries at all. But this actually shows me that the graph has a symmetry of order 4. And here's why. If you look around the outside, there's these 8 points. And so there's this pinwheel shape. And if you rotated the pinwheel shape, then that would give you 8 different symmetries. Except I have to be mindful that there's this connection between 2 of the spokes, if I now, instead of viewing this as a pinwheel, view it as a wagon wheel. But actually, all that's saying is that these particular 2 spokes out of the 4 spokes are connected. Again, remember, there's not a vertex in the middle, and so there's only 4 spokes connecting opposite sides. And so as long as those 2 are connected via one vertex on them, then we'll get that we'll get a symmetry. And so, in fact, this gives you not an 8-fold symmetry, which would be super nice, but it gives you a 4-fold symmetry as long as you keep that x that those 2 vertices in the center lie on, as long as you keep those in the same place. Then for example, quarter rotation, a 90-degree rotation, will keep those 2 in the same place. It'll just interchange those 2 spokes, but they'll still be connected. And so that gives us lots and lots of symmetries. And so I want to make 2 points here. So one is, how many total symmetries does this thing have? In fact, it has 120 symmetries. Which is a lot for something that only has 10 points. And another thing that I want to note is this graph, again, has a bunch of different ways of representing it. This is what we started with. If I say the Peterson graph and draw it, this is the one I'm going to draw. But it just as much could be drawn like this, or like this. And all of these methods of drawing it are equally correct. They all contain the same information. And so it is very difficult, in fact, if someone gives you 2 graphs, to decide whether they're the same graph or not. Okay. Often it's easy to say they're not the same graph. For example, this one has 12 vertices, and this one has 200 vertices. They're definitely not the same. But what is difficult is to, if someone gives you two graphs that are the same, it's difficult to be sure unless you really figure out exactly how to sort of drag the points around to make it true. Okay, so that's known as the graph isomorphism problem. And in general, it's an open problem. It's very difficult to decide if two graphs are isomorphic in any remotely reasonable fashion. But in this particular case, you could just brute force it to see that they are. But I want to come back to this 120 symmetries, because you've been in a combinatorics class for almost a semester now, and probably the number 120 does not sneak by without you saying, wait, I know what 120 is. 120 is 5 factorial, right? I can't not see that 120 is 5 factorial. But it's weird because when I look at this graph again, I don't see 5 of anything. There's 10 vertices, there's 15 edges. Those numbers are both divisible by 5, but neither of them is 5. And there's, say, 5 points on the outside and 5 points on the inside, but there's no way I can permute all 5 of the outside vertices, for example. And so you might wonder, where are the 5 things? So this is a really fascinating question, and I'm about to completely spoil it for you. So if you want to think about this, just stop the video now. This is the last thing I'm going to do in the video, and try and find the 5 things. But if you are busy and have other things and don't particularly want to think about it, I'll go ahead and show you where the 5 things are that are being permuted. Because as combinatorialists, we should believe that every time there's 120 somewhere, there's 5 somewhere. Okay. So, are you ready? I'm about to say it. 3, 2, 1. Okay, I'm going to show you a different picture of the graph, and I'm going to label the vertices here with pairs of elements out of the set 1 through 5. Okay, so I've taken here the set 1, 2, 3, 4, 5. Okay, and so that's S. And my vertex set here, the way I've labeled this, is not S, because S only has 5 things in it. The way I've labeled this actually is that my vertex set is now S choose 2. So the vertices, if you want to think about it, are actually the edges of the complete graph on 5 nodes, 5 vertices. Right? If you want, you really could think of it as the vertices of the Peterson graph are the edges of K5. But then I have to say, okay, well, that's great. 5 choose 2 is 10. But, I mean, why does that help? How did that get us to what we're going? Well, then you have to describe the rule. What is the rule for deciding whether there's an edge between 2 subsets or not? And we've decided here that there's an edge between 2 subsets if and only if those 2 sets have empty intersection. So, for example, at the very top, the subset 1, 2 is connected to 2 things. It's connected to 3 things. It's connected to the 3, 4, 3, 5, and 4, 5, because those are the 3 subsets of 1, 2, 3, 4, 5 with 2 elements that do not intersect 1, 2. Okay, and likewise around here. And so what this shows us is that if you take any permutation of the numbers 1, 2, 3, 4, 5, of which there are 120, and you perform that permutation, that will give you a symmetry of this graph. And that shows you why this graph, in fact, has the spectacular 120 symmetries. So, again, if you really want to relate this back to K5, and remember K5 is the complete graph on 5 vertices, so I'll put this away again. K5 is my complete graph on 5 vertices that looks like this. So there's 1, 2, 3, 4, 5, and I make all the possible connections. I'm not going to try to do this without crossing the lines, because again, it doesn't matter. Okay, so here is our K5. And then what's the relationship between this and the Peterson graph? Well, the Peterson graph, again, corresponds to having as vertices the edges of this graph. So for example, if I pull back up the Peterson graph for a second, this very top vertex is corresponding to the edge 1, 2 here. And so I will highlight that. And then if I look at, for example, again, in the Peterson graph, one of the vertices that this is connected to, well, this is connected to the vertex 4, 5. That vertex in my graph K5 here corresponds to this edge, because again, the vertices of the Peterson graph are the edges of K5. And these two edges of K5 are connected in the Peterson graph because the edges as edges in K5 do not share a common point. So this trivial intersection business or this empty intersection business that defined K5, or sorry, that defined the Peterson graph corresponds to saying, okay, every edge in the Peterson graph is a pair of edges in K5 that don't share a point in common. Okay, we'll wrap up there for this video. Next time we'll pick up and start talking a bit about more terminology that we might use with graphs, and we'll start talking about some things we can prove about graphs. All right, until next time, be well.